Hello, everyone. My name is Vishal Chaugule, and I'm here to talk about an integrated approach that we have established to improve dry powder inhaler performance. Now, to begin with, So as you all know, the inhalation energy provided by a patient is responsible for the entrainment and deagglomeration of drug powder into the airflow. Now, this is a typical DPI, which is a hollow pipe with two tangential inlets at the bottom through which swirl is generated. When inhaled through this device, you have production of particle-laden swirling flow within the device and also emerging from it. Now, these flows have complex fluid-particle interactions, which are dependent on the device resistance and, of course, the properties of the formulation used. We also have the action of aerodynamic forces, turbulence, and particle collisions coming into the picture. So in order to improve DPI performance, it's imperative that we study and understand these complex processes comprehensively. We propose to do that using three complementary methods of in vitro deposition, particle image velocimetry, and computational fluid dynamics. Now, we have used a BDP-based formulation which has coarse lactose as the carrier with a pre-blend of magnesium stearate. We explored 4 different kinds of DPI models, 2 of which have different kinds of tangential inlets. One has 2 and the other has 6, but the total inlet area is the same in both these models. Now, the other 2 models have grids with square holes, one placed at the entry, that is just after the tangential inlets, and one placed at the DPI mouthpiece exit. We use these models for in vitro and CFD studies in air. For PIV studies, which were done in water, we geometrically scaled up these models. Now, the reason why we did so is that we were then able to do PIV measurements at a much higher spatial and temporal resolution than that's possible in air. And that's only because we maintained geometric and dynamic similarity between the flows in air and water by matching their Reynolds numbers. A quick look at the methods. The first one is, of course, in vitro deposition, where we used a NGI cascade impactor with an inhalation flow rate of 60 liters per minute maintained through the device. Now, this is the PIV setup where we have the scaled-up DPI model placed at the bottom of a tank, which has a closed-loop water flow system. Now, PIV measurements were taken in a longitudinal plane outside of the DPI mouthpiece exit using a pulse laser sheet and a CCD camera, which were both in sync. The coordinate system that we used in this study is here. So this is the DPI mouthpiece exit. Coming straight out is the axial direction, and orthogonal to that is the lateral direction. So we have X and Y and U and V as the spatial coordinates and velocity components in those directions, respectively. Now, CFD simulations were performed using ANSYS, where the model geometry mirrored that of the PIV setup, and the computational mesh used a polyhex core structure. We looked at 3 different kinds of turbulence modeling approaches, 2 of which were based on unsteady RANs, and the third one was based on a scale resolving simulation approach, which used SBES. We'll first look at how the CFD results compared with the PIV results. Now, here we see the mean axial and radial velocities at the mouthpiece exit for the 6-inlet model. Now, what we see here is that we have large axial velocities on either sides of the jet center line, and we have a significant reverse flow region within the jet core. And we also see large radial spreading with large lateral velocities on either sides of the jet center line. Now, this occurs because of high swirl in the flow. Now, what we see here is that SBES agrees very well with the PIV results. So we are confident of using SBES to study the remaining models, which are here. So these are the velocities for the other models. Now, the 2-inlet model has velocity similar to the 6-inlet case. But when we use a grid, what we see is that we no longer have those high axial or lateral velocities coming up because of the flow straightening effect of the grid, and it reduces swirl. So the takeaway from this is we are confident of using SBES to look at what happens with the particle and fluid dynamics in the DPI. Now, to start with, so these are the in vitro results. Now, what we see here is that we have a larger amount of the drug retained in the device for the 2-inlet case when compared to the 6-inlet case, but the overall aerosol performance are the same. But when we use a grid, what we see is that when we use a grid at the entry, we have lower mass retained in the device when compared to the no grid case, which is the 2-inlet. But when we use a grid at the exit, we have lower throat deposition. Now, we can explain these aerosol observations first using the PIV results, which are here. Now, these are the flow field velocity contours coming out from those models. What we see here is for the 2-inlet and the 6-inlet case, they're both without the grid. We see large radial spread, and we also see a large recirculation region, which is not good because then we'll have particles moving back into the device. But when we use a grid, we see a much more straightened out flow. So this explains why we see a lower throat deposition for models with the grid. Now, we can also bring in CFD results where we first look at the particle wall impacts within the DPI. So the green line is for the entry grid case, which shows a higher number of particle collisions, which means a better deagglomeration potential. And that's why we see a lower mass of the drug retained in the device for this case. Now, if you look at 1 jet diameter outside of the mouthpiece exit, we see that there is a large radial spread for both the carrier and the fine particles for the no grid case, which is the red line here. But when we use a grid, we no longer see that happening because of the focusing effect of the jet and the grid. So this gives us a holistic view of what's happening with the fluid and particle dynamics, both inside and outside the device, and how we connect it to the in vitro results. So to conclude, we have developed a 3-pronged strategy to assess and improve DPI performance, where we have CFD and PIV techniques playing a supporting role by consolidating the in vitro deposition study analysis. So we are very confident of completely understanding what's happening with the DPI dynamics, both inside and outside. And we've also been able to achieve a good correlation between the particle and fluid dynamics, both within and outside of the device, and connected to the aerosol dispersion and particle deposition that we see coming out from these devices. Now, if you want to read more about our work, you can refer to our papers, which are here. Or if you have any specific questions, you can always reach out to me on my email address, which is here. Thank you very much.
Thank you, Vishal. That was very interesting and a great run through of some different work you've been doing there. I see there's been a couple of questions come through. So firstly, was the swirl quantified and compared between the 2 and the 6 inlet variations that you had?
No, we did not quantify the swirl, but we are doing it now. So because the total inlet area is the same for both those models, and when we define swirl number based on the ratio of the angular momentum to the axial momentum, we wouldn't see, we don't expect to see a difference in swirl. But what we do expect to see is how the swirl is distributed. So we'll have a more uniform distribution of the swirl in the 6 inlet case, but a much more non-axisymmetric for the 2 inlet case, which is what we observe, at least with the measurements that I recently did last week for the 2 inlet model. So we see that the flow is not axisymmetric at all.
Okay, and this is really useful to help understand the airflow and some of the model deposition. Will it tell us much about the interaction with formulations?
Now, the whole point of bringing formulations into the picture is that we need to have aerodynamic forces which are higher in magnitude when compared to the addition and cohesive forces. Mm-hmm. So formulation will come into the picture, but not as much, because let's say we have all these aerodynamic forces and turbulence quantities at a much higher level, then no matter how much adhesive or cohesive forces we have, lesser than that magnitude, we are always going to achieve a good enough deagglomeration without much influence of the formulation properties.
And the final question, thanks, Jeremy, is the model target providing improved mechanistic understanding of performance or in predicting performance? It's doing both, because what we have also understood is that what kind of collisions are happening within the device when we have different kinds of devices which are used, and what happens to the particle dispersion or particle trajectories after they leave the mouthpiece exit. So we are able to understand that, and we can also predict what happens. Let's say when we have, for instance, if we have an idealized throat connected to the DPI mouthpiece exit, so we can predict where would the deposition be depending on what are the trajectories further upstream of the device. That's excellent. Thank you again.
Thank you.